Hello everyone, my name is Reno. Today, I'll be presenting the paper titled ReasonGrounder, LVLM-Guided Hierarchical Feature Splatting for Open Vocabulary 3D Visual Grounding and Reasoning. This paper has been accepted to CVPR 2025. The core task this paper addresses is Open Vocabulary 3D Grounding and Reasoning. This field tackles two key challenges in machine understanding of 3D vision. First, open vocabulary understanding. This means the model needs to robustly understand and process text queries that describe objects implicitly, rather than relying on explicit, predefined labels it was trained on. As you can see in the example, instead of just apple, the query might be something like the red, round, sweet fruit on the table. The model must be able to ground such descriptions and reason about them effectively. Second, dealing with occlusion in 3D space. The goal here isn't just 2D image understanding. We want the model to comprehend the 3D space, much like humans do, based on image from multiple viewpoints. This is crucial because in a given view, an object might be partially or even fully occluded. However, if the model has seen that object from a different angle during its training or scene reconstruction phase, it should still be able to accurately localize and reason about it. The slide highlights this with the accurate localization by the model, even with novel or occluded viewpoints. So, how does ReasonGrounder tackle these challenges? Let's look at its approach, which addresses the two main problems we just discussed. First, for understanding implicit queries, ReasonGrounder leverages the common sense knowledge embedded in large vision language model. As many of you know, has shown remarkable progress recently. By using LVLMs, the model can better interpret the meaning behind implicit queries and specify the target object that needs to be identified. Second, for occluded object localization, to handle occluded objects, the model first reconstructs the target scene into a 3D representation. It does this using 3D Gaussian splatting based on the provided multi-view RGBD images. Once the 3D scene is reconstructed, the model then approaches the problem of localizing occluded objects within the 3D space. Now let's delve into the specifics of the method used in ReasonGrounder. The overall framework can be broken down into three main steps. As indicated on the slide, the first step primarily addresses the implicit query challenge, while the subsequent two steps focus more on handling occluded objects. First, we have LVLM-Guided reference view selection. In this initial step, the system first trains a 3D Gaussian splatting model using the provided multi-view RGBD training images. Then, it employs an LVLM to interpret the implicit query, specify the target object. Crucially, this step also identifies the most suitable reference view for accurately pinpointing that object. Second, the paper introduces a scale hierarchical feature Gaussian field. Here, the model learns to embed instance features and language features into the Gaussians of the 3DGS representation. This embedding process is guided by segment anything model, masks, and clip language features. This essentially enriches the Gaussians with semantic information. And third, LVLM-guided hierarchical grouping. Building upon the results of the second step, this final stage performs a meaningful instance-level grouping of the Gaussians. The system then selects the most appropriate group of Gaussians corresponding to the given view and query. This allows for precise localization even when objects are occluded or described ambiguously. Okay, let's take a closer look at the first step, LVLM-guided reference view selection. As illustrated on the left, the process begins with the given implicit query and a set of training views, typically around 100 RGBD images. First, the model learns a 3D representation of the target scene using standard 3D Gaussian splatting based on these training views. From this learned 3D representation, a top-down view of the scene is rendered. This rendered top-down view, along with the original implicit query, is then fed into an LVLM. The LVLM is prompted to output two things: the name of the target object and an explanation or description of it. Finally, to select the best reference view, the explanation of the target object is encoded using a clip text encoder. This encoded text is then compared against all the training views, which are encoded by a clip image encoder. The view that yields highest cosine similarity with the target object's description is chosen as the reference view. This is essentially finding the view that best matches the LVLM's understanding of the core object. Next, let's discuss the scale hierarchical feature Gaussian field stage. The primary goal here is to learn and embed both language features and instance features into each individual Gaussian. This enriches the 3D Gaussians beyond just their basic properties like alpha, color, and initial latent features. To achieve this, the method incorporates a few key components as illustrated in the diagram. First, supervision generation. As shown on the right, supervision signals are generated from the training views. Segment anything model is used to produce object masks. These masks then help derive clip features, which serve as the supervision for the language aspect, and segmentation maps, which provide supervision for distinguishing instances. The physical scale of object is also considered. Second, 3D feature Gaussian splatting and hierarchical feature spaces. The core idea is to map the initial features of each Gaussian into two specialized hierarchical spaces, a hierarchical language space and a hierarchical instance space. This is done using dedicated language mapper and instance mapper networks, as you can see in the center of the diagram. The hierarchical language space aims to capture semantic information related to language descriptions. The rendered language features from this space are trained using a Hubbard loss against the clip feature obtained from supervision. The hierarchical instance space focuses on differentiating between object instances. Rendered instance features from this space are trained using a contrastive loss against the segmentation maps. Essentially, this stage creates a richer, multimodal representation for each Gaussian, making them aware of both semantic language concepts and distinct object instances within the scene. Let's dive deeper into the supervision generation process, which is crucial for training the feature embeddings. As shown in the diagram on the left, we start with a training view. First, mask generation with SAM. The segment anything model, or SAM, is applied to each training view to obtain initial object masks. These masks are then filtered based on their confidence scores to yield the final mask candidates. These filtered masks are essential for supervising the learning of instance features and creating the segmentation map. Second, clip feature extraction. For each of these filtered masks, a corresponding clip feature is extracted by feeding the masked image region into a clip image encoder. These clip features serves as the supervision signal for learning the language features associated with each object. Third, introducing physical scale. A key contribution highlighted in this paper is the introduction of physical scale. This isn't just an auxiliary feature. It's used as an input for learning both the instance and language features, and it also plays a guiding role during the 3D spatial grouping process later on. As depicted in the lower diagram, the physical scale for each mask is estimated by deprojecting the pixel-wise depth values within the mask into 3D space, using the camera's focal length. This gives a sense of the object's actual size in the 3D space. So, for each mask, we essentially derive a set of features: the mask itself, its clip feature, and its physical scale. These are the core components used to supervise training of the hierarchical feature spaces we discussed earlier. Next step is 3D feature Gaussian splatting. This component deals with features at the individual Gaussian level rather than at the mask level we just discussed. In standard 3D Gaussian splatting, each Gaussian is defined by properties like its mean, covariance, color, and opacity. The formula for a Gaussian GX is shown here. What this paper does is augment the standard properties of Gaussians. First, introducing latent features. In addition to the color and alpha, each Gaussian is also assigned a latent feature vector. This latent feature is randomly initialized for each Gaussian. As highlighted in the diagram, each Gaussian now has its color alpha and this new latent feature. The physical scale, derived earlier, is also associated with the Gaussian in its vicinity. Next step is rendering latent features. Just like color and alpha are rendered into the 2D image space using the standard rasterization process of 3D.js, these latent features can also be rendered. This means for each pixel in the rendered image, we can obtain not only a rendered color, but also a rendered pixel-wise latent feature. The formula for rendering color and these latent features are shown here, involving weighted sum based on alpha values. So, the key takeaway is that each Gaussian now carries an initial, learnable latent feature which can be projected on the image plane. This forms the basis for then mapping these features into the hierarchical language and instance spaces we saw in the overview. Now we arrive at the core of feature learning, the hierarchical feature space, which involves the language mapper and instance mapper. As we've discussed, each Gaussian has its initial latent feature and is associated with a physical scale derived from its corresponding mask. The physical scale and the latent feature of a Gaussian are passed through a lightweight MLP, the language mapper, to produce a language feature. This learned language feature is then rendered into image space. The learning is supervised by comparing this rendered language feature to the ground truth clip features we generated earlier using a Huber loss. An important detail here is that directly learning high-dimensional clip language features with a simple MLP can be challenging. Therefore, the paper uses PCA to reduce the dimensionality of the ground truth clip feature to 64 dimensions before using them for supervision. The language mapper is crucial for ensuring that Gaussian belonging to the same object have consistent language representation across multiple views. Similarly, the physical scale and latent feature are also fed into another lightweight MLP, the instance mapper, to obtain an instance feature. These instance features, once rendered, are supervised using the segmentation map via specialized contrastive loss. This loss, borrowed from the previous research Garfield paper, is designed for 3D representations. It encourages features from Gaussian's belongings to the same instance to be similar and features from different instances to be dissimilar. If you are interested in the specifics of this contrastive loss, I recommend checking out the Garfield paper. While instance mapping helps differentiate Gaussians of different objects, language mapping is vital for achieving constant object-level Gaussian grouping across various viewpoints. Through these two mapping processes and their respective loss functions, Gaussians belonging to the same object in 3D space will learn to have similar representations. This is what ultimately enables effective object-level grouping. We now move to the final step, LVLM-Guided hierarchical grouping. This is where everything comes together to localize the object specified by an implicit query, potentially in a novel view with occlusions. Let's assume that the initial LVLM processing for query understanding and reference view selection has been done, and the scale hierarchical feature Gaussian field has been fully trained. As a result, our individual Gaussians now possess learned latent features that are discriminative for different objects. The process for localizing an object is a given view involves three key actions. First, assign relevancy to rendered pixels. For the current input view, we render the learned language features from our hierarchical language space to each pixel I. Then, we calculate a relevancy score for each pixel. This score measures how specifically the pixel's rendered language embedding matches the implicit query embedding, compared to its similarity with more generic, canonical praise embeddings. Examples of canonical praises include object, things, stuff, or texture. The formula for Ri is shown on the slide. Essentially, a higher Ri indicates that the pixel is more relevant to a specific query rather than just being part of any general object. This helps in pinpointing pixels corresponding to the queried object. Second, select best target scale based on language embedding. Concurrently, we also determined an optimal physical scale, SI star, for the target object. This is done by looking at the mask candidates for the reference view. We find that mask whose language embedding exhibits the highest cosine similarity with the clip text embedding of the overall target object, which was derived from LVLM's interpretation of the implicit query. The physical scale of this best matching mask from the reference view is designed as SI star. This SI star provides an estimate of the target object's actual physical scale. With these pixel-wise relevancy scores in the current view and the target object's estimated physical scale, the system can then leverage the learned hierarchical instance feature to form a target Gaussian group. This group represents the localized target object, enabling a model prediction even when parts of the objects are occluded in the novel view, as depicted in the lower part of the diagram. Continuing with LVLM-guided hierarchical grouping, now we'll see how the actual target Gaussian group is formed. First, generating query-specific instance embeddings. Recall that our instance mapper from step 2 takes the physical scale and the Gaussian's latent feature as input to produce a hierarchical Gaussian instance feature. Now, we use the target object's estimated physical scale, which we just determined, along with the latent features of all Gaussians. By fitting this into the trained instance mapper, we obtain 3D instance embeddings that are specifically attuned to the scale of our queried object. Second, clustering hierarchical feature Gaussian group. These query-specific instance embeddings are then clustered using the HDB scan algorithm. This process groups the Gaussians based on their instance features, resulting in several distinct instance groups. Each represents a potential object or part of an object in the scene. The final step is to select the one Gaussian group that best corresponds to our target object. For each cluster, we can determine its central feature. Let's call it T_I. This central feature T_I can be rendered back into the image space. We then compare these rendered center features of each cluster with the pixel that has the highest relevance score, which we calculated earlier. The pixel most specifically matching our query. The Gaussian group GI, whose rendered center feature Ti shows the highest cosine similarity with this most relevant picture, T hat I, is selected as the final target Gaussian group, GI star. This selected group represents the localized target object, even if it's partially occluded by effectively combining the scale information, instance level feature, and the language-guided relevancy from the query. Now let's move on to the experiment and take a look at some selected quantitative results. Thanks to its approach of learning language features for multi-view consistency and utilizing fine-grained instance features, ReasonGrounder demonstrates strong performance, achieving state-of-the-art results on both the LVLM dataset and the 3D OVS dataset. On the LVLM dataset, if we look at localization accuracy, ReasonGrounder achieves an overall score of 86.7%. This is a significant improvement compared to previous methods like LSEG, LRF, and LangSplat. You can also see strong performance across individual categories like ramen, figurine, tea time, and kitchen. Similarly, for mean IOU on the LRF dataset, ReasonGrounder again shows the highest overall performance at 86.7. These results clearly highlight the effectiveness of ReasonGrounder's architecture in accurately localizing and segmenting objects in 3D scenes based on open vocabulary queries, even when compared to strong existing baselines. Beyond the numbers, let's also look at some qualitative results, which provides a visual comparison of open vocabulary 3D visual groundings. In these examples, ReasonGrounder is labeled as HFGS for Hierarchical Feature Gaussian Splatting. These images demonstrate that ReasonGrounder achieves more accurate and precise localization of queried objects compared to previous methods like LRF and LangSplat. For the ramen query, you can see the RGB input image. While LRF produces a somewhat diffuse heat map and LangSplat also shows some spreads, HFGS clearly and tightly localizes the ramen bowl. These visual examples underscore ReasonGrounder's ability to better understand the query and accurately ground it in the 3D scene, leading to more robust object identification. Furthermore, ReasonGrounder demonstrates strong modal perception capabilities in novel views. This means that even if the target object is partially or even completely occluded in a view that wasn't part of the training set, the model can still successfully localize it. For apple case, you can see two novel views where the apple is occluded by other objects. Below, the unmodeled perception views show that ReasonGrounder correctly identifies and segments the full extent of the apple, inferring its shape even for the hidden parts. These results highlight a key strength of ReasonGrounder, its ability to reason about the 3D scene and object presence beyond what is directly visible in a single, potentially challenging, novel view. That concludes my presentation on the ReasonGrounder paper. Thank you very much for your attention.